Hello Math 1093. In this video we're going to talk about a compelling argument. We will see that that word has a double meaning in just a moment. So again, I've put up the graph of the same function we used in a previous video, the shift and stretch video. This was the graph of, let's see, this is y equals f of x, where f of x is the absolute value of x defined only on the interval from -1 to 2. And what we're going to do in this video is we're going to graph the function g of x, which is defined to be f of 1/2 of x. Alright, so here's what I mean by the word argument. In this particular instance, we call this the argument of f. And there's actually, at least to my way of thinking, not really a meaningful difference between that and the input of f that's being used here. But I want to avoid the word input used in that sense, because I'm going to use the word input to mean the number that we're putting into g. So I need something to distinguish that from what's getting put into f. So we're going to call that the argument of f. And that's going to come up repeatedly as we work out this problem. So what we want to do is we want to graph the function g. Alright. And again, we're going to do this by using a table of values. Now I'm going to set this one up a little bit differently. So this table features x and g of x, and then we will pull in values of f of x as we need them. Alright, so I want to start with what happens when x is equal to 1. Alright, when x is equal to 1, then what do I know? I know that g of x, or g of 1, is going to be, it's going to have something to do with some value of f. But what value of f? Well, when g is 1, then the argument that gets put into f is 1/2 of 1. So that's f of 1/2. So now I have to look at my graph and look at my function definition and figure out, okay, what is f of 1/2? Well, f of 1/2 is, looks like it's 1/2, according to this graph. So that means that g of 1 is 1/2. Okay, what about g of 2? Well, g of 2 is going to be f of 1/2 times 2. So when the input for g is 2, the argument of f that's being used is 1. So I get f of 1, which is equal to 1. So that means that g of 2 is equal to 1. Alright, let's mark off these points in the graph as we work along here. So when x is 1, g of x is 1/2. When x is 2, g of x is equal to 1. And you might think that we need to stop here because we defined f only on the interval from -1 to 2. But let's see what happens if we let x equal to, let's say, 4. I'm going to skip 3 for now and just go to 4. Well, when x is 4, well, g of 4 is the same as f of 1/2 of that. That's the same as f of 2. Well, f of 2, according to my graph, f of 2, by the way, is perfectly well defined. 2 is within the domain of f. And so f of 2 turns out to be 2. So g of 4 actually is defined and is equal to 2. So I can put that in my graph. Alright, now if I were to go further, like say x equal to 6, what would happen then? Well, then I'd be trying to figure out g of 6, which would be equal to f of 1/2 of 6, which would be equal to f of 3. And that, keeping in mind that my domain of f is from -1 to 2, this is not defined. Okay, so I think I really do have to stop at x equals 4, because when my input for g is 4, my argument for f is 2, and that's as far as f goes. So I think we're going to stop here. Okay, we could also put in x equals -1 or -2. Let's say -2, just see what happens. Then g of x is going to be, well, let's see, g of -2 is going to be f of -1. F of -1 is 1. So I can put in a point for that as well. So, if I were to map out all these points, by the way, I'm also mapping out when x is 0, g of 0 is going to be f of 1/2 of 0. That's one instance in which the input and the argument are actually the same. That comes out to 0. Okay, anyway, connecting all these points, I get another graph. Looks kind of related to this other one, this first one, but it is quite a bit different. Okay, so actually what you see here, if you look at the geometry of the blue graph versus the red graph, is the blue graph, everything's been stretched out by a factor of 2. This as well. Okay, now why is that happening? Well, that's happening because anytime I have a point here, x comma g of x, that corresponds to a point on the graph of f. It corresponds to this point, which is 1/2 of x, comma, f of 1/2 of x. And you notice the y coordinates are the same because f of 1/2 of x by definition is the same as g of x. So the moral of this story is, if I want to graph g of x, which is equal to f of 1/2 of x, well, this is the same as the graph of g, or sorry, same as the graph of f, but stretched, in this case, by a factor of 2. Okay, so the point of this video is that this kind of algebraic transformation here, where I put a fraction in front of the argument of f, or put a fraction in front of that x there, that's going to have, I don't know, depending on your perspective, maybe the opposite of the effect that you would think. Like you might think that putting a 1/2 in front of the x, or multiplying x by 1/2, is going to shrink the graph, but it actually causes the graph to stretch out for the reason described here. Because what's happening is, for any given input for any given input for g, I'm referencing what happened to f closer to the x-axis, and then I'm pulling that back out in order to create a point on the graph of g. So anyway, the moral of this video was to illustrate this principle of what happens when I multiply the input of f by a constant. So I want to state this principle in general just because it's kind of the opposite of what you might expect if you're looking at this a certain way. Alright, so here's the rule, or I'll call it the moral. I hate calling it the rule. Alright, the graph of g of x equals f of kx, where k is a positive constant, is the same as the graph of f, stretched or shrunk by a factor of 1/k horizontally from the vertical axis. Sorry, this is getting a little crowded here, but I think I'm done. Okay, so just to re-illustrate how that's happening here. Here, in this case, my k was equal to 1/2. So in this case, k was equal to 1/2. So that means that I'm stretching the graph of f by a factor of the reciprocal of that. So stretch horizontally by a factor of the reciprocal of that, which is in this case 2. All right, and that always works. If I were to replace that 1/2 with a 3, then what I'd be doing is I'd be right here. So if I had f of 3x, I'd be shrinking the entire graph horizontally by a factor of 1/3.